Speaker this week is Samson, who is stuff he's been doing with all his cars on Bayesian inference for gap acceptance. He's at the very end of his PhD, so it should be lots of interesting stuff in the talk. I'll let you take it away.
Yep, thanks, Braden. As Braden mentioned, I'm a PhD student that's hopefully finishing soon, who's been spending too much time looking at cars and been doing a bit of Bayesian statistics. Today, I'd like to tell you a part of my PhD, which is about applying Bayesian inference for gap acceptance model. And these are my collaborators. Half of them are traveling, I guess. So I do want to start by saying that I did draw this in ticks to illustrate what the whole gap acceptance process is about. So gap acceptance model is the sort of conceptual framework that traffic engineers use to describe drivers making acceptance decisions when they are crossing a conflict region. It applies to cases like roundabouts, unsignalized intersections, lane changing, etc. In this context, the traffic stream that has the right of way is called the major stream, and the guys who have to yield is called the minor stream over here. Turns out that a complete description of the gap acceptance process is a little bit more than you saw an opportunity, you press on the accelerator, and you survive. The gap usually refers to the inter-arrival time between the two major stream vehicles. But as you can imagine, there's also other cases, such as this red vehicle here arriving partway through a gap, and hence faces what the literature calls a lag. Or you can have cases where the gap is sufficiently big, so you have more than two vehicles entering in the same gaps in a sort of follow-up process, which is the blue vehicles at the top over there. One of the most important parameters is called the critical gaps, which is defined as which for a vehicle is defined as the minimum gap that it will accept to perform its maneuver. It's not directly observable. We only measure the accepted and rejected gaps, and that's why there's interest in estimating it. In particular, we're interested in estimating the sort of population parameters for the critical gap distributions, usually assuming independent, identically distributed critical gaps. So you're not really interested about the critical gaps of specific drivers. You're also not really interested in, say, the mean of like the 200 drivers that were in your data set, but the mean critical gaps of the whole population of drivers. And just to give you an idea of what a data set looks like, this is a simulated data set where the inter-arrival headway is simulated with what's called bunch exponential distributions, which is supposed to be a little bit more realistic than a Poisson process. It assumes a portion of vehicles are bunched in the sense of they travel very closely to one another in a platoon, so the gaps between them are generally too small to be accepted. So for the figures on the right, for vehicles on the left here, the black density is a true distribution of critical gaps that is of interest. The histograms is the sampled critical gaps for the finite population of drivers in the data set. The dash histogram over here is the dash CDF over there is the corresponding CDF for the histograms, which you of course don't see. What you do see is the empirical CDF for the accepted and rejected gaps, which are the red and blue curves over there. So the whole point of the game is, given the red and blue curves, can you tell me about the black curves? Or at least some summary statistics about it. Before talking about sort of the maths and stats, I just want to say we care about all this critical gap business because it's related to queuing theory, which is used to analyze the capacity of an unsignalized intersections, and is therefore related to things like average delay, average queue length, level of service, and all your complaints about traffic. So there's sort of financial implications in terms of making better investment decisions from better understanding and model predictions and so on. There is a number of critical gap estimation methods usually used to estimate the mean critical gap. The earliest one goes back to Ross, which essentially find where the two distributions intersect. But it's actually quite sensitive to the major stream traffic flow. There's another one called Ashworth's method, which assumes the inter-arrival times exponentials and the critical gaps are normal, neither of which are particularly realistic. And there's a bunch of others, which I didn't list here, because there's these two papers that did a bunch of comparisons between them. and show that most of them are biased anyway. Turns out the best one here is the one that's highlighted in red, which is the maximum likelihood estimator, and that's the one that I'll be benchmarking against. And I will talk a little bit more about it later. There are two major criticisms for the existing estimation methods. The first is that it assumes drivers are consistent. Consistent in the sense that they always accept the first available gap that is greater than the critical gap and reject all preceding smaller gaps. But as you all know, people are weird, and there are cases where a vehicle rejects the gap and then subsequently accepts a smaller gap. The second criticism is that most of the methods usually make a parametric assumptions on the critical gap distributions, usually log normal with the positive support and bright skewness, which is actually not a particularly strong criticism because there's also studies that show that the parametric assumptions doesn't make that much of a difference to your estimates of the mean and standard deviations or critical gaps. But in any case, we'll try to address both of these in this talk.
So, Samson, you're assuming a specific driver has a fixed critical gap
Yes.
you're drawing from that parametric distribution.
Yes, that's right, that's right. So each driver actually has just one realization of a critical gap, and that realization sticks with them for their whole life. As the talk gives away, we are going to take a Bayesian approach. For those of you who are not familiar with Bayesian inference, you will know Bayes' rule very well. So I like to think of it as a relentless application of Bayes' rule. There's some unknown quantity denoted as theta over here, which doesn't really matter if it's state parameters or latent variables. In Bayesian statistics, there's only really unknowns. You describe your uncertainty about it with what's called a prior in orange, and which encodes your uncertainty and knowledge about the unknowns before seeing the data. When combined with the likelihood in black via the Bayes rule, which the likelihood is the statistical model, you obtain the posterior in blue, which is the unique way to reallocate probability mass that is compatible with your updated state of knowledge after having seen the data. It's a very sort of flexible framework, but the conceptual simplicity usually lies in the difficulty in computations. In a nutshell, distributions as an infinite dimensional object is hard to work with. So easier if you have samples from it, which calls for efficient and universally applicable sampling algorithms. And that's where you will see phrases such as Markov chain multicolor or MCMC for short getting thrown around in the literature. As always, you start off by writing down what a statistical model looks like. In this case, I indexes the minor string vehicles, so there's capital M of them in total. J indexes the available gaps each vehicle faced, going from 1 to n sub I. Each vehicle should probably face at least one gap to tell you something about the data. But it could be the case that a vehicle faced a gap, did not accept it, because the observation period ended. That will also tell you something. So the statistical model looks like this. Under parametric assumptions, the critical gaps are the given some parameters phi, which is usually y is of interest. Tij is the jth gap vehicle I faced, and Pij is the corresponding probability of accepting it, which is modeled as a function that depends on the critical gap, the available gap, and possibly some other parameters. Zij is a corresponding binary acceptance decision, which condition on P will just be a Bernoulli likelihood. If you assume the drivers are consistent, then your acceptance function here will just be this, where I is the indicator function, so you have a degenerate Bernoulli. In this case here, this doesn't account for the sort of lags and follow-up dimension at the start. It only really considers gaps, but it turns out that if you work through the maths, they will have essentially the same conditional independent structure, so we'll just focus on this gap acceptance model here.
Sorry, so your gap is a time?
Yes, yes.
And they've got a perfect knowledge of speed.
Yes, yes. You can always criticize and add more covariates into the model, but yes, that's the idea.
So you're assuming, basically, you're assuming the major stream is that movement at constant velocity, is
No, no, no. Yes, yes. Between two vehicles, yes. Yeah. So usually when you talk about gap acceptance, it's at the moment that the vehicles arrive in front of you and how much time left before next vehicle arrives. Yeah. if you are not so happy about the conditional IID assumptions on the critical gaps, then I do want to take this opportunity to tell you about sort of the real assumption being on exchangeability of the driver's critical gap. Exchangeability, in my opinion, in Bayesian inference, is a bit like, what's it called, shadowing lemma in numerical integrations, where you don't really need to know it to do the things that you do, but you probably should if you want to know why things work. So a finite collection of random variables is exchangeable if the joint density is invariant on any permutations, which essentially tell you that the label tells you nothing. And you can certainly think of that might not be true for every cases. If you knew the first driver was Zara and the second driver is Michael, then you probably have different prior assumptions of what their critical gaps might be.
Yeah, if you see Zara drive, you should just shoot someone.
That's what I'm talking about. What's remarkable that there's these theorems that tell you that if you do make an exchangeability assumptions, then you could and you should model things as conditionally IID, which in my opinion is probably the coolest things about Bayesian statistics and justifies things like putting priors on things. Anyway, so the data consists of all the available gaps, all the corresponding binary acceptance decisions, and also which vehicle faced which gap implicitly defined by the indices. The unknowns here is the critical gap distribution parameters, which is usually what's of interest, possibly parameters that are in the acceptance functions, all the individual critical gaps, and all the sort of event-specific probability of acceptance. In the last two cases here, those are the sort of like things that you don't know and probably don't really care about, but they are part of the inference problem. And that's how life usually goes. There's only a few things that really matters, but a lot of other things just get in the way. If you make a usual sort of log normal assumptions, then the distribution of parameters are mu and sigma. And since you're interested in the mean and standard deviations, there are some functions of mu and sigma, which is given by these equations over here. The maximum likelihood estimator, the MLE popularized by this gentleman called Trollback, assumes drivers are consistent. So all you really need is the accepted gap and the largest rejected gap for denoted as AI and R sub I for vehicle I. Under parametric assumptions, the likelihood is essentially that for a intervally censored data, so which is essentially the probability of the critical gaps lying between this interval. And the log likelihood, which is the logarithm of this line, and that's what you work with when you work with sort of probabilities, is then given by this. If the vehicle did not reject any gaps, then R sub I is usually set to 0. Once you make a log normal assumptions, you can substitute the CDF or the log normal in. Condition on the data, this would just be a function of mu and sigma, which all of you already know how to do, to optimize it to get the maximum likelihood estimator. So find the partial derivative, set it equal to 0. So I won't bore you with the details because I didn't do it either. In this case, the problem is simple enough that you can just run a numerical optimizer on it. So that's what I did with quasi-Newton LBFGS, and things will converge very quickly. If you do it, it's probably a good idea to reparameterize sigma into log sigma, so you can run the optimizer in unbounded space. For all the subsequent discussions, when I compute some MLE, I restarted it 10 times and pick the best one, so it's unlikely that things get stuck in local optima. For the Bayesian approach, this is the sort of model that we are focusing on. We also make a log normal assumptions on the critical gap distributions. We replace the acceptance function by this logic link. Turns out that you can do Bayesian inference on sort of the consistent model with the step function, but the sort of more modern gradient-based MCMT sampler won't really work very well on that. And we'll show that the logic approximation doesn't really make that big of a difference. So if you look at this and it's basically just logistic regressions, then yep, essentially. So you also have unknowns in the sort of predictors here. And these are the priors I used, which essentially gave me sensible numbers in the sense of not having critical gaps that are in the order of 10,000s. So all posterior sampling is done with the Newton sampler, which is an adaptive version of Hamiltonian Monte Carlo algorithms. And for some of you, you will know this much better than me. And for the rest, instead of bombarding you with a bunch of equations and algorithms, I will show you how things will look like visually with these sort of beautiful animations. So when you try to sort of sample from the distributions, which is shown as like a banana over here. Its density defines the surface in the space. To have a sampler is the same as saying you want an algorithm such that the amount of time that it spends in each region of the space is proportional to the volume. So the older styles of the metropolis algorithms, that's like this one random walk behavior, where at each iterations you make a proposal nearby, accept it probabilistically, and does it in a way such that if you did it correctly, the Markov chain theory tells you that you will converge to sampling from these distributions. The issues with running this metropolis sampler is that you are essentially making small steps in the neighborhood of your current state, and that's why it's not as efficient. So the whole idea of non-Newton sampler and Hamiltonian multicolor is to implicitly simulate some sort of Hamiltonian system so that at each iterations you can move very far while still maintaining a high acceptance probability, and therefore resulting in sort of more efficient sampling. So I think this is a sort of very nice illustration. In any case, when you run sort of these gradient-based MCMC sampling algorithms, you have to compute this term at some point, which will turn out to be the gradient of the log posterior with respect to each of the unknowns, and that's where we have a bit of issues with the step functions. Unless you are writing your MCMC algorithms or you are learning about it, then it's probably a good idea to sort of implement your Bayesian models and do posterior sampling with some form of probabilistic programming languages, usually something like Stan. I did mine in PyMC for some other reasons. And I also use another package called Arvis to do the post-processing of MCMC samples. And this is what the result looks like after running sort of Bayesian inference for one simulated data set. So for the figure of here, on the left you have the marginal posteriors, on the right you have the trace plots for each of the parameters. So the mu, sigma, and beta. The vertical lines and horizontal lines there correspond to sort of true parameters. Since you are sampling from the joint posterior, you also have the distributions for each of the individual critical gaps. So I have shown the first three over here, so you can do sort of driver-specific inference, although the local parameters is usually not of interest. There are a few things that you probably should do to make sure that your MCMC ran correctly. The first one, if you're not sure what you should be looking for, your trace plot here should look like white noise. Hopefully not because you ran things for a million iterations. You want your effective sample size, which is in these columns here, to be as high as possible, and your R hat to be close to 1. And all of them look great over here, as expected, otherwise I wouldn't be showing them. If you do sort of statistical methods, Bayesian or not, then a lot of the times you will hear phrases like uncertainty quantification getting thrown around. If you're an advocate of it, I think that's amazing. If you prefer sort of point estimates, big data, machine learning, I think they are very useful as well. So I won't try to convince you otherwise. But if you take a Bayesian approach, for each of the unknowns, you have the sort of full posterior distributions to which you can quantify different level of uncertainties. So the first two columns here are the mean and standard deviations of each of these distributions. And then the third column is the 95% HDI. HDI stands for highest density interval, which is the shortest interval that contains the nominator amount of posterior mass. But reporting uncertainty in terms of mu and sigma is probably not the most intuitive for traffic engineers. What you can do is to propagate your samples through the equations for the mean and standard deviations for the log normals to get uncertainty in terms of the mean critical gap and standard deviations of the critical gaps. So in this case, the MLE and posterior means are pretty close and pretty much spot on for the mean, underestimate the standard deviations a little bit. You can also propagate the samples again through the density of the log normal to get the sort of point-wise 95% credible intervals on what the distributions looks like itself. I've also overlaid the histograms for the samples of critical gaps that were actually drew in the data set, so you can see a bit of sampling variability. And that's all cool, and that's been sort of the standard things that you get out from running a Bayesian analysis. And this is what the sort of moneymaker plot looks like. As per in good spirits of good applied mathematics, you just do it a bunch of times. So what we did was simulate 100 data sets at each level of major stream flow, going from 100 to 1300 in the sets of 100. So the traffic flow, major stream flow increases this way. Although you do have the whole distributions for the posteriors, In this case, we just summarize it by its posterior mean to get a point summary, and therefore you have something that is comparable to MLE. The blue dot here, the blue circle is the posterior mean. The red crosses is the MLE. The points are sort of roughly aligned with the corresponding major stream volume and jitter horizontally a little bit so you can actually see them. On the left side here, you have the situations where the critical gaps follow log normal distributions, just as both estimation methods correctly assume so. On the right side, or maybe the other way, but on this side over here, the critical gaps actually follow gamma distributions with the same mean and standard deviations, but both methods still make a log normal assumptions. So there's a bit of misspecification over there. There's a few things that we can see. The first one is that the posterior means and the MLE are pretty similar, and both are sort of fairly unbiased for a wide range of traffic flow, in the sense that when you take the average across the sampling distributions of the data, you get something that gets it right on average. The second thing is that the sort of parametric misspecifications with the gamma doesn't really make all that big of a difference, which is in sort of an agreement with existing literature. And lastly, probably the most important part is the sort of shapes of the points that you're seeing, where your standard error is higher and it decreases and then increases again. So that's the part that I did not expect a priori. But it turns out that this is also the only sensible way how you should behave under a fixed observation period. So at low major stream flow, your data looks like a bunch of acceptances. They're all very big gaps, 30 seconds, 50 seconds, and so on. They tell you virtually nothing about where the decision thresholds really are. And that's why you have a lot of uncertainty. Things get a bit better when the major stream flow increases and you face a bit more rejections and you can figure out where people's thresholds really are. When the flow increases so much to the point that it becomes very hard to find safe gap, then that's when you have vehicles waiting on average for quite a while before entering the conflict region, and your data set simply has less vehicles and your standard error increases because your sample size goes down again. There is this paper in critical gap estimation literature that talks about a desirable property for an estimation method to be equally reliable. But for fixed observation periods, equally reliable estimator is probably unlikely. If you are doing sort of like a Bayesian approach, then you are interested in more than point summary. But it's also, the question is also not about reporting a 95% interval, but rather you want to report the 95% interval that you report to someone is actually useful in the sense of it does 95% of what it's supposed to do. Although Bayesian credible intervals are influenced by priors and therefore don't generally need to have the correct frequency coverage the way confidence intervals do in frequency statistics. So coverage in the sense of when you get a specific data set, you can do your methods, apply your magic, and then get a 95% interval out. Does that contain a true value 95% of the time? If it does, then it has the roughly correct the frequency coverage. And that's what we're showing here with the coverage of the 95% HDI for each of the data set. If things look right, that should be sort of all around 95, and looks pretty good to me, maybe except for the standard deviations of gamma when Q is equal to 100. The next thing that we then try to do is to sort of address the existing criticisms of the criticism of existing methods. And the first one is concerning about the inconsistent behavior, and the basic answer would just be jointly estimate the critical gap distribution parameters and any of the inconsistency parameters. Although the logistic link that I use sort of have this sort of inconsistency built in, as a test scenario, we consider a sort of more convoluted inconsistency model where the probability of acceptance depends on not just the usual safety margin term, but also on these additional terms where Sij is the time span, the vehicle span has been at the U line, which is illustrated by this figure over here. And the idea is that when the vehicle first arrives at the U line, you haven't had the time to assess how crazy the oncoming vehicles are. As time progresses, you have a bit more time, make more sensible decisions, and therefore your probability of acceptance asymptotes towards like a step function. So what we then try to do is to simulate data according to this inconsistency model and then try to recover the parameters. You have mu and sigma, which is the usual sort of critical gap distribution parameters. And you have the beta naught, beta 1, beta 2, which are the sort of inconsistency parameters in this link function over here. And you have the mean and standard deviations, which are, again, induced by the mu and sigma. The black line here is the true values, and the blue curve is the posterior after having generated the simulated data of 30 minutes. So in this case, yeah, you can do a bit of joint inference, although you have a lot of you still have a lot of posterior uncertainty. In particular, for beta 2, which is the coefficients concerning the time span at the U line, there's still a lot of posterior mass near 0, so you can't really conclude that if that term actually has an effect. So the next thing that I would do is to crank it up, generate sort of 8 hours data, which is probably not the most realistic thing, but your Bayesian posterior will concentrate as you expect. So you can do sort of joint estimations, but probably the more practical question is what would be a sensible inconsistency model in the traffic modeling scenario, and whether you actually have enough data to reliably estimate all the unknowns to a useful level of precision. The next thing that we then try to do is to address the second and perhaps more challenging assumptions of criticisms, which is to relax the parametric assumptions on the critical gap distributions. So in essence, instead of estimating the sort of finite dimensional phi, you want to estimate the distribution itself. The frequentist approach to non-parametric density estimations is with something called kernel density estimate, which all of you probably have used at some point. The Bayesian approach, at least one way to do it that I saw on YouTube, is with the Dirichlet process mixture model. I know not everyone spends a lot of time looking at a bunch of distributions, so we'll start off with everyone's favorite. You have the binomial model as a sort of canonical way to model independent coin tosses. And the parameters there is usually P, which is the probability of success. If you were to put a prior on it, then you need a distribution that has a unit interval as its support. And it turns out that the beta distributions is a good choice. It's a very flexible family, contains specific cases like the uniform, as shown over there. And turns out to be conjugate prior for binomial, so there's a bit of computational convenience. If you want to extend things into a multivariate case, multivariate in the sense of you have capital K greater than 2 categories, then you can do it. You will need to specify the probability vector here for each of them, or maybe one number less. But the multivariate generalizations of the binomial is called the multinomial. If you look at your PEMF over here, it looks basically like the binomial term over here, except with more terms in the products. The corresponding generalizations of the beta is called the Dirichlet distributions, which now defines the distributions over probability vectors. Its parameters here are the alphas. So, and the diagrams over here is the case when capital K is equal to 3. So you are sampling from the 2 simplex. And as you change the alpha values here, your density of sampling a different probability vector changes. And that's all cool. Why am I telling you about all of these things? So now we're ready to define what a Dirichlet process is. In essence, a Dirichlet process is a distributions of distributions over some measurable space. If you are not too familiar with measure theory, I'm certainly not myself, then omega is a sample space, which is just a set. The calligraphic F is the sigma algebra, which to us is just a collection of well-behaving subsets of omega. And unknown distributions have a Dirichlet process prior, denoted as this line over here, and has parameters alpha, which is a positive real number that can be interpreted as an inverse variance, and another parameter G naught, which is a base distributions on omega. Just like Gaussian process, if you're familiar with that, the properties, or the defining characteristics of the Dirichlet process is in terms of its finite dimensional counterpart. If you take any finite partition of the sample space, there is an induced Dirichlet distributions. So what does that mean? This is visually what it looks like. The sample space here is the reals, and the base distribution is the standard normal. I chop it out into 4 parts. My standard normal assigns a certain amount of mass to each of the partitions. Okay. If I can draw a lot of samples for my Dirichlet process, each of them being a distribution itself, and I look at the amount of mass each of the sample assigns to each part here, then that will follow a Dirichlet distributions, as per this line here, where the parameters of the Dirichlet is defined by the amount of mass the base distributions assigns scaled by alpha. That's so cool. That such thing exists, and turns out that is true, and that's where a lot of these major theoretic papers try to prove. One very useful property is that it has this conjugacy property, where if you put a Dirichlet process prior on unknown distributions, and you have a sampling model that looks a bit funny, but that's exactly what it means. The data, given the unknown distributions, has that distributions, then the posterior of the G is also a Dirichlet process, which you can see is essentially like a convex combinations of the base distributions and the empirical distributions. And that's great, but what does the Dirichlet process actually look like? And there's a very nice constructive algorithm called the stick breaking process, which I did not make the name out, that tells you how to generate a sample from a Dirichlet process. You start off by sampling the individual point masses from your base distribution. You then construct the weights in a way that resembles stick breaking, in the sense of you draw a bunch of random variates, beta random variates. The first weight that you have, so you start off with a stick of length 1. The first weight that you have is the first beta random variates. And the second weight that you have is the second beta random variates times whatever's remaining. So you keep going on like this, and at each time here, you are essentially piling off a little bit of the stick. That's why the name comes from. When you take the weighted sum of all of these, then that will be a sample from a Dirichlet process. And that's what this figure is showing here. The dashed line is the base distributions, in this case, still a standard Gaussian. The orange lines, each of them is a sample from the prior. The data they collect is the empirical CDF here, which is shown by the solid black step functions. And then the posterior is shown in blue, which the samples in posterior, which essentially is a compromise between the prior and the data. You might look at this and think that it looks pretty ugly. There's a bunch of jaggedness. Turns out that that's actually not too big of an issue, although by constructions, the samples will be discrete with probability 1. It turns out that any distributions can be approximated arbitrarily or pointwise by a sequence of samples from the Dirichlet process, much like how the rationals is dense in the reals. But if you're not happy about it and you make further smoothness assumptions on your unknown distributions, and you want to estimate its density, then that's where you will convolve it with a continuous kernel, where I have denoted as H over here. It's usually chosen from some parametric family, which essentially results in a sort of infinite mixture model. It does lose the conjugacy property, so computation will be harder. Then that's what we'll do to sort of non-parametrically model the critical gap distributions. In this case, as you use a normal kernels, and the Dirichlet process prior is placed on the parameters of that normal. If you want to sort of infer this unknown density, then technically you do need to store infinitely many weights and component parameters. But what you can show is that the expected number of components with non-negligible posterior weights is of order log n, where n is the number of data points. And for us, it will be the number of critical gaps here. So you usually don't need to keep that many. So the common approach, which I also use, is just to truncate it at some sufficiently large k, where in general, the truncation error will not be more significant than the simulation error from running MCMC. And that's what we did here. So in this case, I simulated data from the mixture distributions, or a bit mixture between normal and log normal. The normal here is this bump over here. The log normal is the second bump over here, where if you have a bimodal distributions, it will be definitely outside the support of the log normal. And this is where I imagine a case of this sort of non-parametric modeling might be useful. Indeed, it doesn't look really neat, but the non-parametric prior, the DP, the Dirichlet process mixture prior, which is on the left over here, is able to sort of pick out the two bumps. And although there's quite a bit of uncertainty around the modes. So the log normal, the usual log normal assumptions on the right, is doing its best to fit the two bumps. This is what the sort of posterior distributions looks like for the mean and standard deviations of the critical gaps. The left side is, well, the right side is. You have the Dirichlet process mixture prior and the log normal on the other side. the short answer is they look pretty much the same. So the whole sort of Bayesian non-parametric stuff, very cool. And if you are interested in inferring sort of the latent critical gap distribution features, for instance, you might want to draw some inferences about the subpopulation of risky drivers and conservative drivers and so on, then it will be useful. But if the goal is only really to estimate the mean and standard deviations, probably doesn't really worth all that much to go through the hassle. The last thing that we did is to apply it to sort of real data. Not because I think that's what applied in applied mathematics refers to, but because it's what your reviewer will always ask for. So in this case, this is the vehicle trajectory data collected at a roundabout in Perth. So my sort of collaborators, they fly these drones over the roundabouts, filmed it, run some sort of machine learning algorithm to extract the trajectories of each vehicle, from which you can calculate all the sort of gap acceptance data. So in this case here, we have a 3-legged roundabout with 1 entry lane each. And we have sort of 2 sets of recording, which is what I'm calling flight 1 and flight 2 over here. Capital M is the total number of minor stream vehicles. And this sum over here is the total number of gap acceptance events, which by definition has to be at least M. M star in here is the number of inconsistent vehicles. Those are the guys that were looking at their phones and rejected gaps and subsequently accepted smaller gaps. What we then have also here is the mean, the 2.5, 97.5 percentiles of the accepted gaps, and then for the rejected gaps. Yeah.
If this is a roundabout, how can it have a major lane? Like, does your setup rely on there being a lane
Yeah.
that has right of way, a lane or something?
Yeah, so for every lane over here, it will be its or minor lane, and the major stream traffic is the circulating floor. Yeah.
So the actual roundabout itself is the major. So it would be like circulating. Okay. So the cars that are in the roundabout.
It's like a bunch of teams.
Yeah, exactly.
So you've got some topology. You can read. It's like what is it? That a roundabout is the same topology as a cloverleaf or something like that. Yeah, roundabouts.
This is why Perth drivers have so much problem with roundabouts.
Because of March or
Yeah.
I get it.
Thanks. Yep. So this is what the, hopefully this table gives you a bit of idea of what the sort of gap acceptance data looks like. And the estimates are summarized here. So what you're seeing is a bunch of posterior for the mean and standard deviation of critical gaps for each lane and for each flight. The thinner line here is the 95% HDI. The thicker line here, which is a bit hard to see for some of them, is the sort of posterior quartiles. So it's the middle 50% posterior mass. The normal triangle is the posterior median, and the field upside down triangle is the MLE.
Probably worth saying what the lane is.
Sorry?
It's worth explaining what the lane, by lane you mean each road roundabout.
Yes, each leg only has one lane, so that you need to identify.
So you shouldn't have any fingers for the
Yeah. Oh, in this case, we're only really looking at the entry lanes. Yep. So the mean critical gap is generally around 3 to 5 seconds, and the standard deviations is around 1 to 3 seconds, which seems somewhat plausible to me. The MLE and the posterior median is sort of very similar, especially for the mean critical gap. Maybe a bit more difference there for the standard deviations.
Sorry, Samson, is there a difference in the timing of the two flights? Is one like
Yeah.
an hour and one back or something like that?
So yeah, that's a really good one. So the flights usually the reason we have 2 flights is actually because when you fly the drones out, the battery doesn't last that long. So you need to come down and then change the battery again. So it's usually sort of a few minutes in between. Yeah. Yeah. So as you all know, when you do sort of like real data, you don't really have the true parameters to sort of benchmark against and see how well your methods perform. So what we then try to do is some sort of validation strategy where you fitted model to sort of flight 1 data as the training data, use the fitted model to predict the empirical accepted and rejected gap distributions for the flight 2 data, which essentially means computing these long integrals that I just managed to fit onto the slide. The results for lane 3 is shown over here, where the thicker dashed line here is the validation data that we observe. And the sort of shades around here is not because your eyesight is turning bad. Each of these lines here is a sampled from the predicted distributions at the top here. So in this case, there are 200 of them. If your model is sort of performing okay, you will hope that the prediction is sort of in line with what you observe. And that is indeed the case here. So probably the sort of simple Bayesian model that we're working with is not the worst thing in the world. So in conclusions, we try to sort of construct a Bayesian approach to the critical gap estimation problems. And when summarized by its posterior means, it does achieve comparable performance with the state-of-the-art MLE method. We also show that the sort of equally reliable estimators in terms of having the same standard errors across all level of traffic condition is probably something that is unreasonable to ask for. We also show that the Bayesian approach has well-calibrated uncertainty quantification in terms of having the roughly correct frequencies coverage. Lastly, we extended the Bayesian methods to try to address existing criticisms by incorporating inconsistent drivers and to relax sort of the parametric assumptions on the critical gap distributions. Here are the references that I managed to squeeze in, and thank you for your time.
Samson? All right, do you have any questions?
So my experience, I've used theoretical process mixtures before, like dramatic, because I find it really hard to know, but I find that they fail a lot. So do you need a lot of data when you do that?
Yeah. So this one here, the ones I have, is probably like a sort of 2 hours data, 2 hours observations that are simulated.
Okay.
Yeah.
Because I've always ended up just using finite mixture models instead of infinite mixtures.
Yeah.
You have some control
Yeah.
over it by just fixing the number of components. So I'm glad you got it to work.
Maybe got it to work.
Yeah.
Yeah. So the whole MCMC definitely is a bit sort of uglier. You get lower effective sample sizes. Yeah.
Great.
Can you, and this will work, can you talk me through the thinking behind the Hamiltonian sampling and the what's the what's the thinking behind?
So
We finish next week sometime.
yeah. So if you want to have an efficient sampler, what you want is that you can start somewhere and then go very far, but still accept it with high probability. In the sense of, when you run sort of the Metropolis style sampler, you usually have two issues. The first one is that you're making the step size are too small, so your chain sort of crawls around, a bit around. The other one would be you make the size too large, and then if you check the sort of Metropolis correction criteria, because the probability of acceptance is depend on sort of the ratio between the densities. So if you make too large, you will jump to some density that is very low, and therefore almost surely will get rejected. So what you want is then some sort of methods that somehow can move very far, but still accept things sort of frequently. And the HMC stuff does it in a way that set it out correctly in terms of satisfying the conditions so that your chains still have the correct limiting distributions that have exactly that properties. Implicitly, what happens is that, where's my slide? Yeah, so if you remember sort of the Hamiltonian system, when you move along a trajectory, the Hamiltonian stays constant. If you can construct it such that that Hamiltonian is the density, then you can move sort of along the trajectories and still have that Hamiltonian being essentially the same. Therefore, your acceptance probability is still very close to 1. And that's what it does by sort of doing these auxiliary parameters, adding things in with higher dimensions, but somehow able to construct a Hamiltonian system behind the back. Yep. But I do have a ton of references if you are interested.
The rough intuition
gradient of the probability distribution is information that you would want to take into account. This is one of many methods that takes into account that gradient. So that gradient can tell you which direction you might be able to go. Like it encodes that shape to some extent of the distribution. So you don't just sort of go in any possible direction, you go in the direction favored by the gradient. That's not what it's doing exactly, but it's why it works well.
My intuition that it makes sense to me is if you imagine you have a banana-shaped bowl and you kind of flip marble with no friction with some sort of random force behind you for it, the gradients kind of keep you in the bowl and get you around the corners of the way. So like, if you imagine that's what's happening now, it's just like a banana-shaped bowl. You can see when it tries to get out of low probability, in low probability regions.
And now you just have nice balls rolling around.
It's a lot.
Yeah.
You want to take a big step. You don't want to go in a straight line because you just somewhere else.
It's just a
Or not.
that's straight around the run, yeah.
Order and roll.
So we mix that with this one. But it's actually a fault.
Right. Do you have any other questions?
Is the critical gap, why was it by mode? We know that there are two classes of people there.
So
Bizarres.
I'm not saying who's belonging which to which component. So this part here is sort of the simulated data where I was saying, okay, these might be the situations where you actually want to do some sort of non-parametric modeling because it clearly is outside the support of the log normal. So this is what I simulated, and I thought it was somewhat sensible assumptions about you having sort of different subpopulations of drivers.
Was there any evidence? Is there any evidence of bimodality in the actual data?
I haven't actually looked at the critical gaps, but I suppose that's part of the issue is that you don't know what the critical gaps really are, and therefore you're trying to do the inference on those. I didn't really have the courage to run this sort of non-parametric stuff for real data. I do not believe that the data that we have is enough for that.
My assumption would have been that it would be
Yeah, unless you're doing it at 11 o'clock on Friday night.
but the picking people up.
People are not getting picked up.
Yeah.
Well, it can't be zero. So at least it's got a truncated zero. So that it can't be normal.
Okay.
And
But I
that-
meant,
Symmetric.
yeah,
But as per what Mike was saying, there's also the whole issues of when you sort of extract the data and calculate the gaps, there's a bunch of subtle issues associated with when we sort of identify the vehicles over here, then that's when each vehicle has sort of a bounding box, and then we try to calculate times between them. That's where, you need to find out where the vehicles actually arrive at the U lines or not. So there's a bunch of subtleties associated with that.
Would it give baseline not just be an easier thing for an algorithm to pull out gap types from?
Yeah.
Like from just the image recognition point of view?
Yeah, absolutely. The reason is because this is the data set from another project where they are doing things for roundabouts. I'm interested in that, and I thought it's a nice application. Yeah.
Sorry, I know I'm done. Why are you rejecting the individuals that are accepting the smaller gap time after they've rejected the? I feel like that's exactly what I did. Was pressure behind me built up, and I panicked that I should have gone then, and I didn't.
You mean this column over here?
Yeah.
Yeah, I didn't. So they are part of the data set. Even if a vehicle did not accept any gap, so they only rejected a gap, that still provides some information to you about where the critical gaps are. Maybe not a whole lot.
The vehicle's still there?
Yes, the vehicle is still there.
To this day?
No. The vehicle moved at some point. Otherwise, I don't think it will survive on the road.
Yeah.
Yeah. I'm saying it's in the data set, But this is sort of evidence of saying they are drivers like Shannon. Yeah.
Alright, should have time for another question.
That's the last one question, which I probably should have the answer to. But, I know the roundabout data, you've got some big roundabouts as well as small roundabouts.
Yeah.
Here you're looking at a single lane, 3-lane roundabout.
Hmm.
Have you done the same thing for the larger roundabouts? Might be different or different approach?
Yeah.
2 lanes coming in, et cetera, et cetera.
So I did try to look into that, and that's when the part of this idea of checking the data quality in a bit is a bit trickier, especially for the sort of when you have bigger roundabouts and they're having 2 lanes. When we sort of try to calculate all these gap acceptance available times, then that's where you need to find, essentially how far vehicles are away. If you have 2 lanes next to each other, sometimes there's sort of false identification saying this guy accepted a 0.02 seconds grab, but in essence, it's just 2 vehicles sort of entering at the same time. So there's a bit of issues with the data over there, and that's one of the reasons why I decided to sort of stick with single lane roundabout.
There are no more questions. Thanks, Samson, one more time.
Yeah, thanks everyone.
There will be no seminar next week because there is a colloquial one instead. So, a couple weeks.
But you do know the exact.
I still don't. Yeah. Yes, yeah. It's like, well, I think it's kind of interesting.
You'd be great. You can be very sure.
Very happy.
I've done something that's really creative. At the end of the day.
And we got that one. You know, necessarily didn't happen in the
I did mention I've got, I meant to have
No,
got this earlier.
that's all good.
Thomas was who I was genuinely reading.
No, it guys deflecting it.
I know that guy.
No. It is this one thing where it's just,
I bet that guy's written a paper. It's like, I don't know.
I came to set out.
Seen that.
Oh, it's absolute. It's a personal pet peeve that I've directed it effectively towards Thomas and Gopal for the entirety of my But
Fair enough.
well, just every engineering or oceanographer or anything, it's like, oh, it's in my calendar. I don't forget things. It's